Yeah, just a minute.
Hello, good afternoon, good morning.
Yeah, good morning, Professor. Just a minute, Professor. We'll start it.
Going to start now or?
Just a minute.
Okay.
Yeah. Hello, everyone. I welcome you back to the lecture 10, which is on wind farms and microgrids. Yeah, I'm without delay in the lecture. I'm just handing over to the Professor Saad to deliver the lecture on the wind farms and microgrids, which is continuation of the last lecture.
Thank you very much. Thank you very much, Dr. Shiva, for the introduction. So let me share the screen. Okay, entire screen. Screen one. Share. Then yeah, I think we stop somewhere here.
Yeah, it's Professor.
Okay.
It's fine.
Okay, thank you very much. So I think we stop here, for this, I think for the 6-phase generator. I think we stop in the 6-phase generator. See, we see the fixed phase generator configuration with 12 diodes and 12 switches here for the voltage source converter, and then with 3 boost converter, leaf boost converters. Okay, and then also we may sometimes to increase the power also in the synchronous generators with the indirect wind turbines. So we may have also 6-phase generators, and you can see with the 30 degrees phase shift between each one of them. So that like this actually will enable us also to handle higher power. Okay. Yeah. Again, for the multi-windings configurations of generators. Okay. Synchronous generators and distributed power converter stages. So you can see here, converter 1, converter 2, 3, and 4. We have 4 converters, and that's been used for multi-stage and distributed gearbox with maybe different speeds. Okay, multiple high-speed shafts. That's actually also increase the power. Okay, now let's go to the summary of all of those what we have seen so far. And then we can see the comparison actually between all these configurations, and maybe give you some, some idea actually on this. So if you still remember, let me take the. If you remember, okay, the wind turbine type, we classify them based on either fixed speed or variable speed. Okay. So under the fixed speed, I think we have seen a number of what you call, especially the synchronous generator, power converter topology. There is no, okay. Converter capacity not applicable. Okay, speed range. Okay, less than 1%. Okay, soft starter. Yes, it has to have soft starter. Gearbox. Yes. Aerodynamic control. Yeah, active stall and pitch for the blades. External reactive power compensation, yeah, is needed. I think we have seen it with the capacitors. And active power control and MPPT is also not visible. For variable speed drive, for variable speed wind turbine, we've seen a couple of them. So we've seen with the different what you call topologies, but what you can see here, in terms of converter, either sometimes we use full and half, like here, for example, small, reduced, full. Okay, actually this full, I think there is an issue here. When you're having a full power converters, actually, what does it mean? The inertia of the system will be reduced significantly. Okay, and you can see most of them will have the active power control, which is good, and that doesn't require any active power compensation. Okay, also the pitch control all applied. Okay, and the gearbox. Okay, gearbox, yes. This is you can see for the last two, it is especially for the permanent magnet signal generators. It is an optional. It's not required. That means we can run it without signal. So this is just a summary of the types. As I said before, if you want to have more details, actually you need to go in each one of them, and we study one by one. Okay, let's look into the control part. I think that's quite the most important maybe part in the wind energy systems. So let's start with the defect. Okay, so I think we have seen this topology before. Okay, so we have the power converters, and then the stator is connected to the grid, and then we have the two converters, either the rotor side and then the grid side. Okay, so in this quarter we have 3 levels of control. Okay, control level 1, which is actually rotor and grid side control. Okay, level 2, which is wind turbine control strategy, and then level 3, which is the wind turbine integration grid strategy. So because this is a defect, so we have the grid control, the rotor, because the rotor grid control, the wind turbine itself, and the integration. So what we do in level 1, okay? What the level 1 do actually? Level 1 mainly do the regulation of the power flow between the grid and the generator. So that's the level 1. And what you can see here, we through the control of the switches that we supply to the inverter, okay, we can control this. And then level 2, control the amount of energy extracted from the wind turbine. Okay, so we control the amount of energy by the turbine rotor. So that's actually level 2, how much power we can extract from the wind turbines. And then what you can see here, the input for this stage is the omega and beta and the wind, v-wind, the velocity of the wind speed. So because this is in charge of the wind turbine control, for example, in case we have an MPPT control, so we need the wind turbine. Beta here, beta is the pitch angle in case the wind speed is very high, whatever, so we control. And then here we have the omega, which is the shaft, rotation, so control. So this, and then from those control units, so we will provide the V-bus reference, Q generator, QS the apparent power, and the active power, and what you call the torque. So that's to provide it to the level 1, and the level 1 then we generate the control required for that. The level 3, okay, level 3 responds to the wind farm or grid center control commands for megawatt dispatch, voltage, frequency, or inertia control. So the frequency, the voltage, and the power factor, So that's actually provide in level 3. So there are 3 levels of control of the defect. So if you look into, we zoom to the first, what you call, level, and you can see here we have the V bus reference and the Q reference, and then the control of the first one, and you can see here the switch. You know, we can switch between this and that, and then the control. And then here, this is in charge of the DC bus voltage control by the grid side. Okay, and then here, which is the active torque and the Q control, that is done at the DFIG. And then here we control the rotor voltage and to achieve specific torque and the reactive power that is required from the grid. Okay, I think it's very important to understand how this works. We have to understand what you call the wind turbine power curve. Each wind turbine has a wind power curve. And this power curve consists of 4 regions: region 1, region 2, region 3, and region 4. And as I mentioned before, the x-axis is the velocity, or the speed. So we have V, velocity here, which is cut in. And then here we have V, which is cut out. Okay? And here we have the mechanical power. Okay? Mechanical power. So if you look into this wind turbine, it moves from region 1, which is when the wind is below the cut-in speed, and that is not useful. Okay, and then we if the wind passes the wind speed, the cut-in speed, then we can see there's here an increase in power. Depends on the wind speed. As the speed increases, the wind power will be increasing till what you call it reaches the rated power, and this is what you call the rated power. Within this region, then it will stay constant because that's the rated power of the wind turbine, and that is actually for a range of speed. Okay, for a range of speed, maybe between, for example, 15 to 20 meters per second. Depends on, as I say, depends on the wind turbine. Okay, and then if it exceeds that wind speed, then it will what you call cut out, means it will shut down the wind turbine. Okay, within this region, I think this region is very clear. There is no power here. There is no power, and then what we have this range where power is being generated. Within this region, okay, we need to what you call track the maximum power. Okay, and if you look into this wind turbine, and you can see here the wind turbine speed, and here the wind turbine power, and you can see at a different speeds, for example, 6 meters per second, 7.2, 8.4, 9.6, 10.8, and so on, 12, 13, and 14. So on this curve, on each curve, there is one operating point, which is the maximum power, which is, for example, for this curve here, yeah, this is the maximum power for this point. Okay, so at the 1.2, okay, PU, okay, per unit nominal speed. Okay, so it gives 12 meters per second. This is the power, maximum power that can be extracted from the wind turbine. Okay, okay, so this that's why here in this region here is the need for the what you call the MPPT to work to attract the maximum power, because the power will be variable and changeable. Okay, okay, I think that's important. So why do we what you call maximum power point tracker, which is actually located in level 2. I think we have seen here. Remember, we take the wind speed here, okay, and then from this wind speed, and then we have beta, which is the pitch angle, and then here there's actually the control that's in charge of the MPPT. So let's look into here. sorry. So the control of the variable speed wind turbines, okay, when it's rated, wind speed is achieved by the controlling the generators and maximum wind power captured at different wind speeds. So we have a different, like I say, there is an optimal tip speed ratio, okay, which can be achieved by attracting the power. So for a given wind speed, each power curve has what you call it a maximum power, MPP. I think I have mentioned this, at which the optimal speed ratio, WBT, is achieved. So we need to find this point. And this point is always located at the tip of the wind speed curve. And this is how it looks like. So we have, like I see before, we have the cut-in speed. And then, for example, at different speeds, there is one MPP, and then maybe move here to another MPP, you know. So what does it mean? Means when the wind speed changes, the control algorithm should be able to move to the next MPP. That's what the MPPT do. And when it moves, is number one is how fast it moves to the next MPP, and then does it have any oscillation around the MPP? That's very, very important. You know, one of the characteristics of the MPPT, you know, is to make sure that actually it does move fast, okay, and without any oscillations. And this is a bit tricky, because to move fast, you need to increase the step. And when you increase the step, means you may miss it. It means you have to go back. So that's the oscillation. Okay. So because when, for example, I want to move from this to this, okay, there are two possible ways. Either I reduce the steps, and then when I reduce steps, I take longer time to reach to the next MPP. But if I make the step bigger, I can reduce the time, but I may miss it. So I need to, the oscillation, for example, it's here, not here, then I jump here, and then go back here, maybe, and then jump here. So this is what you call the oscillation. So these are the two main characteristics that's actually we use. Okay. So between the constraint between the steps of change, the speed, and the oscillation. Because this is a two, because the oscillation reflect on the power oscillation later on, okay? And the speed means maybe we lost the power. Sometimes we may better prefer to lose some power rather than having power oscillation. And if you look into this curve, you can see it's also controlled or divided into three modes. First one is the parking mode, which is before the cut-in speed, all right? And then we have the generator mode, where I think we mentioned it just now. Yeah, here, this region. And then we have the pitch control. Here the pitch control means we have to adjust the what you call the pitch. For us, maybe the speed is too high, then it's been reduced. Maybe sometimes we may even use the braking system. Okay. And the parking mode is when the speed is below the cut-in speed, okay? And then the generator control mode is when the wind speed is between the cut-out speed, rated speed, okay? Okay. And the pitch mode is for higher than the rated wind speed, but below the cut-out speed. Because cut-out means you have to, the power is kept constant, okay, by the pitch. I think this is, I think I have mentioned it just now. Yeah, this is the area. All right. All right. Okay, good. So pitch control mode is for higher than the rated wind speed, but below the cut-out limits, okay? And when the wind speed reaches or exceeds the cut-out speed, the blades are pitched completely, okay, out of the wind, and and no power is captured at this time. All right. All right, good. So maybe there are different, same like we have seen in I call it in PV systems, there are a number of techniques. Some of them are sensor based. What does mean sensor based? Means we use the sensors to sense the what you call the parameters, like for example the swing speed, all that parameters. Or there are some sensorless techniques, such as the hill climbing, the PNO, and so on and so forth. There are a number of them actually used in so this is how the MPPT looks like. Okay, so if you look into this, you can see we take the wind speed, we measure the wind speed here, we have sensors, and then it goes to the MPPT, and then it gives you the omega reference, and then we'll adjust the control. So that's actually how the MPPT works for this. Okay, this is measurement wind speed. So here you can see here, then we will have the wind speed, and then the MPPT profile. All right, and then supply, and then we control the power converters. So for different configurations, this is a hill climbing. Okay, so this is the first one is power signal feedback. This is a hill climbing. Also the same. We takes the speed of the what you call the high speed shafts speed, and then do the iterations for the MPPT, and then provide the control, and then control the converters. So there are quite a number of actually methods, actually the same like methods. Even now we have the AI based, the PSO, the what you call there are quite a number of methods actually for the MPPT control. So, but as I say, it's the most common one is this one. The most common one still used in industry is this: the hill climbing, the PNO, and the chemical conductance. Okay, and most of them use the sensorless because that's cheap. Okay, there are a few issues actually, or a few issues on the wind power. I think there are some of them which we have discussed earlier. Any questions so far? Please feel free. At any point of time, if you have any questions, please feel free to interrupt and ask the questions. Okay, wind plants. Okay, as you know, output varies with the wind resources, and this cannot be dispatched like any conventional. So, for example, you cannot dispatch certain amount of power from the wind turbine at any time you want. So the system operator cannot control the rated power. The rate of power decrease or increase, RAM or whatever, due to the fall of the wind speed. So this is because it's due to the input, which is the wind speed. So in some areas, large amount of wind generators, wind variability can have significant impact on the voltage profile. That's actually the impact, actually, what we see, especially if you have large wind in the system. But in microgrid, we don't have this kind of issues, as I said before, because this is small system. We're talking about unless we're talking about utility scale microgrids. Usually that's actually quite large. But if we're talking about campus or residential or community, I call microgrids, we have no problem with this kind of issues. This is actually when they refer to utility scale, So because the dynamic of individual wind turbines and the entire wind farms could have significant impacts, because even when you're having a large wind farms, you have different wind turbines, and different wind turbines, they operate at different what I call speed and different power will generated. So that's actually double fed induction generators and induction generators with full converter interface doesn't contribute to the system energy, and that's actually the big issue. Okay, because it's purely power electronics driven, and that's the issue of all the power converters. And that's why, and yesterday I mentioned one example of Denmark. They achieve almost more than 50% of their electricity generated from the wind. But how they achieve that? They achieve that by storage. Okay, so because they have a certain amount of wind, a lot of capacity, certain time, which exceeds the need, and then they have storage to provide that. And they want to achieve the 100% by 2035, but also by increasing the storage. Without storage, you will never able to achieve 100% all the time. It's impossible. Okay. So with the present wind turbine designs, they don't contribute to frequency regulations. However, as I say, nowadays there are many many regulations that actually needs to be in place to try to regulate. So common issues of grid integrations, I think we mentioned most of it. Wind cannot be managed, okay, and then wind plant to trip, causing cascaded failures to total collapse of the grid. But like I say, small distributors in grid, so if it falls, then that's cascade the whole grid, especially if they represent quite significant amounts of what you call power generations. Okay, with the energy imposes, there is a high cost in terms of reserve and storage. So, like I said, again, we go back to the storage. So that's actually one of the solutions that can make wind and even in microgrids works. So impacts on voltage stability and also the network as a whole. Okay, that's why just now we mentioned it is one question on the faults. So we need to consider the wind turbines as part of this. At high wind energy penetration levels, the inertia of the grid system decreases. I think that's especially with the full converter wind turbines. Okay, all right. So that's a big issue, but as I say, there are other ways on how we achieve. So increased reactive power consumption can lead to voltage instability if the transmission network is weak, especially towards the end of the networks. Let's give you some scenarios, some examples. Maybe this is because we've seen a lot of writing now. Let's see some of the examples. So why do we need? You can see there is a high impact of the wind on the grid. So one of the ways why we need one of the ways finding ways on how to address this issue, and one of them is wind power forecasting. Okay, so this is one of the way, because that's actually will give us the indication on how much wind or how much wind power we expect. And it's needed by many players or many stakeholders in the electricity networks, and we will see them after this. Okay, if we look into, for example, and the main reason of why with this wind forecast is to provide a schedule of expected generation, because this is the question actually to be answered. The question is the expected generation, which we don't know. But also we have the meteorological conditions. These meteorological conditions are sometimes very hard to predict. Very hard to predict sometimes. Yeah, sometimes we may get it right, but sometimes we get it wrong, because there are many other factors which affect this. So you have two extremes. What you call this? Something which is uncontrollable. You have no control of it, and then you want to have an expected specific amount of power generation that you expect from the wind turbine. So you're looking for something specific with something without specific and not controlled. Okay, so let's look into this an example here. We see the load maximum, which is 100%, and then we can see here the grid load without wind turbine. So the grid load is here. It goes back and then drops, and then goes and drops. So this is a profile. Maybe it's keep changing, okay, up and down. And then grid load without wind turbine, and then with the wind turbine. Okay. So what you can see here, you can see the blue, the red one is the same. You can see the blue one, what happened? The residual load due to the renewables. Sometimes it goes high, sometimes it goes big. You see, highly variable. And sometimes even go below zero, So what does this mean? It means actually, yeah, it's very highly uncontrollable, So it's very, very, very hard to control. So if we can predict the amount of power that's generated from this wind or from these all renewables, that actually can help stabilize the grid. And how does the wind, prediction looks like? Okay. So, for example, schedule containing, for example, maybe 24 to 96 values per day, all right? Single plant or aggregated, okay? And then you have a confidential band, where, it's like an error, margin error, So here is the measure, and this is the delivered prediction. You can see we can actually almost predict. Okay, but still there is a lot of gap. There is, for example, there is an error here. Here's the errors here between the delivery predictions and the measured one. So this is the errors. So that's why I say the predictions is dependent on meteorological data, and this meteorological data may not be accurate, and that's actually the one of the issues. Okay, so why these power predictions is needed and who need them? Okay, I think the most important one is the grid operators, either at the transmission or at the distribution. Okay, and that will help them to balancing between the different sources, dispatch and redispatch, load flow calculations, and congestion management. So that's why the grid operators needs those predictions, so it can give them more accurate, more informations on how to make a proper load flow calculations and congestion management. Also, energy traders, the ones selling and buying, traders, trading wind power on energy markets. So they want to know how much power tomorrow, so they can charge. Okay, because they make money by selling and buying. So, and that influences the renewables energy on stock markets, price. And also energy traders, and then also the wind farm operators. Okay, wind farm operators also actually very interested in this, because they know to schedule maintenance. For example, they will expect that the next couple of days there will be no wind. The wind speed is below the cut-in speed, so that's the time where they can do the maintenance or repairs, whatever they have. Okay, and then send the schedule to the grid operators. So that's actually the why or who will be interested in forecasting or prediction. We call it prediction or forecasting of the wind turbines. And in this forecasting, there are quite a number of ways or scales how we do the prediction. Anyway, maybe it's 30 minutes now. Any questions so far?
Sir, I have one question.
Yeah, please.
This forecast, short term, medium term, and long term, Is there any standard would specify this duration, or it is based on industry experience?
Yeah, this is based on different people will define this differently. What is the short term, and even now we have the very short term. The very short term, the long short term, the medium term, long term. So, but basically, anything that between 0 to 6 hours is considered as short term. Okay. And something between 6 to 48 hours, which is 2 days, we call it a short term. This is a very short term. The first one is very short term. Okay, this one is short term, and then we have medium term. Okay, so anything between 6 to 48 or 2 days is called short term. Between 2 days to 10 days is called medium term, and then also we have a long term prediction also. So, but here in this table, actually, we want to show the stakeholders that is involved or affected by this. For example, if you are looking for something between short term, then we have the traders, because they sell immediately, the energy markets. Okay, yeah, it's controlled immediately. Yes. Okay. Any other questions?
Nothing, Professor.
Yeah, but even sometimes, even you can have not short term, an immediate or on current, actually, now. You want to know now, the predicted now, what will be the power. So, but this one requires a lot of data and a lot of these models or this prediction method or forecasting methods, actually, it helps a lot in predicting the amount, but sometimes it may go wrong, and many times it goes wrong, the predictions, because as I said before, it depends on the meteorological data, and the meteorological data are not, certain, So these are the stakeholders that we call interested in. Okay, so for short terms, the traders. Okay, here we have plant operators. Okay, grid operators, load dispatch centers, and so on and so on. So different parties, interested in this forecasting or predictions to maybe. I just want to show you another. Let me stop here. Slideshow. This guy. This one. Yeah. Some of them I just showed just now. So why the power predictions is necessary? So I think we mentioned just now. Who needs them? I think we answer this. This is very important. Who need this? Okay. What are the recommendations to implement the forecasting? So like short term, very short term. How does the power prediction works? And then why it is difficult. So I think this is what I've shown just this graph just now. We have seen this. This is for photovoltaics. Okay. Okay, and these are the who won this. I think we have explained this one just now. Yeah, we have explained this. Just want to show you. Yeah. Let me. Okay, so yeah. So for example, if you have a numerical, one of the ways is to how do numerical prediction works. You see. So starting with taking like a Google map for certain locations, and then divide it into gridded locations, and then different resolutions, use different resolutions for different grid, and then start zoom with different resolutions, and then we can define the distance, between the different grids. For example, here it's around 40 kilometers region, this area, and then this is 9 kilometers here. And then, like I see before, you see, before I mentioned, I see the grid points. These are very important. And then this is the site. to be forecasted. So we select the site, and then we see the distance for grid for connections, because defining the site, it has to be not only based only on the wind speed, as I mentioned before. It has to be also dependent on the grid and the load. Okay, there are two things. When we want to do a site, yes, we can do a site selection, what you call site survey or whatever at different locations, but also, yeah, we have a good site with a good wind speed, but it is very far from the load center. Okay, if it's far from the load center, it's fine. Is it very far from the grid connection point? If yes, how much it costs to do grid extension to that location? If it is too expensive, then just forget about it. Okay, so because grid extension is quite expensive. Okay, so but if the site location, that's why we start surveying with this kind of parameters. Okay, load centers and the grid connection. So that's very very important. Okay, and then I think I mentioned just now about the wind. Okay, so it affects the height. With the height, the wind speed will change. I think we have explained this, and this is how it works. Okay, so we take weather, what I call classifications, and then weather data for previous speed. We take the wind speed, whatever, and then we do the prediction. Okay, and then because there is a weight factor according to the capabilities of different weather situations, so different one will have a different weighting. Okay, weight like objective function. Well, I don't know, you know the objective functions, which each parameter has what I call weight. For example, certain data which has been very accurate, that when we give it very high weight. Another one which is based highly variable and we are not sure about it, we can give it a lower weight, and then you can get the wind power predictions. So this is benefit of the combination, for when you have different models. So what you have, this is the measured one, the green one is the measured one, and this is the different models which give you the prediction. So you can see some of them actually can predict, and then you combine them, then you can have a very almost an accurate wind power prediction. Okay, this is for solar, and sometimes it's difficult, I think, because the errors in meteorological forecast, very common, error in power transformations, and sometimes is unknown power plant. We don't know the power plant, and this is some examples. Wind power availability below 100%. Okay, so this is below 100%. Forecasting errors due to unknown power plants. So, and then this is wind farm shut down due to the grid congestion. So you can see the grid, the power. This is the dark blue is the what I call wind. So here is shut down. In some of the parts. Okay, I think maybe stop here. This one, then we go back to the slides. Go to this one, lecture 3. Put on slide mode show. And then display presented mode. Okay. Okay, there are some solutions actually for because we said that actually the forecasting is solve the problem of predicting the amount of power from the grid, but also for the grid integration there are also other solutions to the wind plant for grid integrations. So one of it is necessary, reactive power to the asynchronous generators, which are able to absorb continuously the power produced. Also, power electronics, okay, can be used for grid integration for wind power plants. this. Sorry. So power electronics. Where is it? Power electronics can be used for grid integrations of wind power plants. Provide the grid managed services, control of active power, reactive power, and then strengthening the grid by the control of effective values of voltage and frequency. And as I said before, most of the inverters now are grid forming inverters. Okay, they are grid forming inverters. What does it mean? It means they are not just responsible of injecting what you call active power and reactive power compensation, but also they are responsible on voltage and frequency stability. Okay, but as again we come back again to the microgrid. Microgrid, we have less of the issue, but using the grid forming inverter in a microgrid actually makes the system almost perfect. Okay, because it's small system and it's able to control it easily. Yeah. Most of grid codes, okay, all I think also very important here, the grid code. I think very, very important that all of us works on this have to study the grid code for the interconnections of wind power plants. Okay, output of wind plant also may be treated as negative load in the grid. Okay, which may result in I call it deeper valley, or deeper valleys in things. Okay, also what you call okay, this is actually important. Wind power plants should have also the ability to control, regulate the voltage. Okay, and then installing interconnection to the transmission grid by installing devices such as the VSC and the STATCOMs. Okay, so this is also, I think, quite important. Okay, I think this is for protection. I think this is one of the questions just now. So rotor current protection. Okay, limit the current in the rotor side of the converter. Okay, if the current rises above the set values, usually we use a crowbar is activated, and that's short circuit the rotor windings. Okay. Typically, in this case, voltage at the terminals of the generator decreases rapidly. I think that's a very good use of the short circuit. And then, in order to overspeeding turbine, okay, speed reference of the pitch is reduced simultaneously. So we use the pitch to reduce the speed of the things. Okay, and pitch angle, so that reduces the mechanical power. And last one, which is if we have this does not work, and then we have what we call the rotor protection, which is the disconnect from the grid. If the speed of the rotor is high or lower than the set values, then we for a certain time, then we disconnect, and then disconnect the grid from the grid also if the voltage is above the limits. So this is actually, that's what I say. Most of the renewables have the capability of the connect and the disconnect from the grid. Okay, all right, good. Yeah. Why do we need the fault right-through capabilities? And this is a requirement actually. Okay, especially in we have a large disturbance. Okay, which leads to very high fault current in both stator and the rotor. Okay, and this voltage, especially on the rotor side, voltage source converter are less tolerant to the high currents. Because these converters usually, as you know, they are semiconductor materials, made of semiconductor materials. They are very sensitive, and they have limits, very tight limits on the voltage and current capabilities. So if the fault current that goes back to this will damage them. Okay. further energy or additional energy can go to the charge of the DC bus capacitors, and the DC bus voltage rises rapidly. So this is some disturbance. And that's why some of researchers or some applications where they put in the DC bus another storage, which able to absorb this amount of energy. Okay, and this may lead to the tripping of the unit if this energy is not managed well. So it is a need for careful assessment and the proper design of the control to improve the capability of managing those faults. Some of the ways, one of them is the temporary reduction of the active power. Okay, one of it is to what I call active power is ramped down to a predefined limit. Okay, or reduction on the active power with active power boosting, so increase the terminal voltage or improve which we're able to improve the stability. So these are the fault right through capabilities of wind turbines. So I think basically this. Let me maybe switch to another one. We have almost an hour now. So any questions, please? Before we, any questions at the moment?
So one question I have with respect to grid forming and grid following. So usually I understand the inverters we deploy for either wind or solar that is grid following in nature. But nowadays, grid forming also coming to discussions, and there are some standards which says that probably down the line they will form also a quite significant percentage of inverters on the total installed base. So I just need to understand, sir, is there any discussions or standards or probably some sort of guidelines to decide if I take 100% inverter out of that, what should be the typical range for grid following and grid forming in sort of percentage, if I say? Is there anything, or how will we decide how much percentage of inverters will be grid forming? Because we cannot have all the grid forming.
Yes.
Yeah.
Very true. Yeah, I think the current because the current percentage between it's like 70-30. 70, which is grid following, 30% will be a grid forming. That is a good percentage. However, like I say, there is even grid forming inverters. Now there is a way on how to make this inverter actually work as grid forming and grid following. You got what I mean? Means through the control systems, you can form this inverter to work as a grid following or as grid forming. Depends on the grid condition. Okay, this is the most recent one. It means that we have like an inverter which has dual mode of operation. Okay. But currently it's 30-70, which is quite common practice, which is quite so far it works well in few, but we see that in the near future there will be more what you call more grid forming inverters actually being connected to the grid. Maybe the percentage will increase significantly.
Okay. Got it. So, sir, with respect to hardware, is that remains the same for grid following and grid forming, Only the control part which plays the role?
Yes, it is the same. The hardware is the same. It's an inverter. It's the same. It's all the control part. Yeah, it's all of the control. Yeah, that's why I say there is what you call in some. It's still not yet in industry, but in research already we have some what I call inverters which can work on both mode. Depends on the grid condition. Okay. Any other questions? Okay, maybe we to the next presentation. Yeah, I think.
Professor.
Yes, sir.
There is a question on the chat box, Professor.
Oh, okay. Where is it? Sir, while sizing the standalone microgrid powered by solar, PV, and battery, is it necessary to predict the solar, PV power, and why? Yep. If again, I think we yesterday we have gone into this in not yesterday, on Saturday. I think we have gone into this in detail on sizing. You know, so how to calculate the actual sizing of the PV. You know, and it can start with just pencil and paper till we do all the calculations, and then very rough calculations. We calculate the load, and then from the load we know the number of PV panels we need, and then we have the number of batteries we need, and then I think I have given an example yesterday. And then I given another example where we go into detailed calculations, where we include the losses due to the dirt, due to the mismatch, due to the temperature, due to different factors. So it depends on if it is your microgrid, you know, it is something which is, you know, it's supplying a non-critical load, supplying something which is, like example, light, supplying something which is not critical, and if it goes off, there's no problem. Then maybe what you call a solar prediction may not be necessary. May not be necessary. I say may not be necessary. But if you want to do a proper, you know, very detailed analysis or detailed calculations, then that's actually a must. Okay, means you want to do very precise calculations, because, for example, yesterday we said if we have two PV panels, and then we put these two PV panels together. So one of the losses that exists is the mismatch losses. Okay, and this mismatch losses is due to the manufacturing tolerance. Okay, so in accurate calculation, we need to include this, and I think I will, in the lecture, I will share it with you how to do this. But if you want to do, you know, rough calculations, then you don't need the prediction. You don't need the mismatch losses. You know, but maybe just like we want to design a water pumping, you know, for remote areas or small homes. You know, maybe may not the power prediction, but power prediction helps an accurate system design. That's my answer. Okay, any other questions?
No questions.
Okay, so maybe we move to the next part.
Yeah, hi, Shumesh.
Hi.
Yeah, I think this one. Yeah. Yep, I think this one. So let's present. Okay, present. Entire screen, screen one. Share. And then come the PowerPoint. Screen. Full screen. Display setting. Yep. So the next 30 minutes that we have, we'll be focusing on what is the future technologies for wind turbine configuration? So this is actually also quite important, topics, because knowing where this technology is heading actually will help us in doing the proper planning, especially if you are like a power engineer, which you are interested in installing wind farms or whatever. So we will look into first one on the future generation in terms of generators and the drivetrain. Okay, so where the future will be leading on this, and then we will look into the power electronics, because in the wind turbine there is a large amount of power electronics components inside. Okay, and then in terms of transformer, because the transformer also is a large, because the wind, that's actually the wind turbine. The wind turbine consists of the rotor, but the rotor is mainly materials. It's not our area of specialization, materials, and then how they design it, and so on. But from the electrical part, we are more interested onto a generator, the drivetrain, power electronics, and the transformer, and then the grid. And then we will look into the semiconductors, because semiconductors plays an important role in what I call in these systems. Okay, in terms of generators. Okay, in terms of the generators, actually, the multi-stage gear drive. Okay, we used to have a single stage gear drive. Okay, so the future will adapt to moving further to a multi-stage gears rather than what we call a single stage. Okay, so this is they have a very high robustness. Okay, and then also cheaper in price. Okay, and then to adapt to a different rotational speeds, because we have the wind speed actually operate at different rotational speed, that will help. Okay, and a multi-stage gearbox. Okay, which is normally heavy and bulky, has to be used in this kind of operations. So multi-stage box has been troublemakers in many wind turbines because it's noise and downtime. So this is one of the issues. So moving forward is using the single or one-stage gearbox, okay, which actually have some trade-off solutions between single stage and so on, for 5 to 8 megawatt wind turbines. Okay, they are simpler, and then also compared to a multi-stage. And this is how it looks like. Okay, you may have multiple low-speed signal generators. This is how it looks like actually. We call it a direct drive. Okay, so we don't have any gearbox. I think this is one of the issues. This is the issues of the gearbox, like we said before. The issues of the noise, the issues of maintenance, the issues of size. So moving forward, actually, it's to move to even with no gearbox or direct drive. Okay, and this is growing up even to megawatt level, to 10 megawatt level. Okay, it's difficult to get acceptable size and weight for multiple generators, but I think it will be one of this is one of the new directions actually. It's direct with low speed generators. Okay, in terms of power electronics, I think there is a new also a lot of innovations on power electronics, and this is driven by the limited space available within the wind turbine. So we have a limited space. So what does mean limited space? Means you cannot have big converters or what you call multi-stage converters and so on. So full-scale converter solutions that avoids a bulky low-frequency transformers is necessary. Okay, so one of the solutions is to remove the low-frequency transformer from the system. Okay, at all, because as we know, the low frequency transformers scales with the power rating. So as it goes, as the power rating goes higher, then the transformer will, especially I'm talking about the low frequency transformer, I'm talking about the 50 hertz or 60 hertz. Okay, so removing these transformers, that actually can reduce a lot of space inside the nacelle of the wind turbines. Okay, back to back. Okay, this is another topology, back-to-back cascaded H bridge converters with galvanic isolation, DC-DC converters as an interface. This is one of the ways. Okay, this is how it looks like. So what's happened here? This is the future technologies for wind turbine conversions. So you have back-to-back, okay, AC to DC, and then you have you can have an MFT, a medium frequency transformer, not even a high frequency transformer. You know, medium frequency transformers, and then you connect to the grid. Okay, so you have from the generator, from the generators, and then you connect to the grid. You know, so this is what we call very common cascade bridge with medium frequency transformers for wind turbines. And the good things about this here is you can have an N cell of this, and they are all similar to each other, you know, so compared to the multi-level topologies. So DC-DC converters also have a medium frequency, okay, medium frequency operating at several kilohertz, 2000 kilohertz. Thereby, the transformer size can be significantly reduced. We can reduce the transformer size significantly. Okay, with the cascaded structure, yeah, this is the key. With the cascaded structure, it can be directly connected to the distribution networks, which is 10 to 33 kV, with high output quality and filterless design. So this is the good things about this new what you call topologies, you know, which is the cascaded. You know, if you cascade them, so we can increase, the what you call the voltage level, and then you can connect directly to the what you call to the 33 kV what you call grid line. So also future topologies includes the modular, and that's a good thing. Also the modularity. Modular multi-level converters. It's a multi-level, but it is a modular in nature. Okay, so also that's another one. See here, like here, we're having a few three-phase connected together, easily scalable. That's a good thing. Sometimes we have one wind turbines, and then we want to add or we want to increase the power. Okay, and then voltage power capability. See, they have quite high power. And then the output filter can be also eliminated because of the number of levels. When you have the multi-level topology, actually the number of what you call total harmonic distortion can be significantly reduced. Okay, so this, but again, the challenge is the devices that we use in this modular or these converters, you know. So the challenge is what are the devices that is available in the market that help us to use this. So we go back again to the basic, which is the switches. Okay, which is the backbone of the power converter. The switches are the backbone, you know, because all these converters actually is a combination of different what we call switching. You know, some of them recently we've seen what we call not recently, I think 10 years ago now, almost 10 years ago, which is the silicon carbide, the GIAN devices actually, which able to handle high power, high switching frequency, and also high current and high temperature. Okay, So, and always the question is which one better, is to use the IGCT or the IGBT, So, these are the questions. So, because, this will determine the cost of the wind turbine, what is the efficiency of the wind turbine, how reliable is this wind turbine, and how modular is this wind turbine. So this is because if you have a modularity, actually, that helps actually, I call, in case you want to increase or in case there is a fault. And this will also allow us to do the, what I call, the fault tolerance, because most of this power electronics also have the capability of providing fault tolerance. The fault tolerance actually is important in case, for example, when you have a cascaded, like I go back to this one here. If you have, for example, a cascaded topology, and then one, for example, this goes faulty. So this can still function, but maybe with the reduced quality of power. Maybe the total harmonic distortion maybe will increase a bit. However, the system will continue run. This is what we call the fault tolerance, because that's the objective of having the modularity in this kind of systems. Okay, so that's why modularity and what I call scalability and fault tolerance is becoming an issue. And as I said just now, the silicon carbide, which is making a revolution actually in the power electronics converter design, in terms of all the performance. So if you look into the comparison between the IGCT and IGBT, as I mentioned just now, IGBT have a higher switching frequency than IGCTs, okay, which is means able to switch at a higher frequency. Because the IGCTs usually they are quite big in size, okay, large in size, and they have high electromagnetic emissions. So cooling problems, they have an issue with cooling problems. And in terms of lifespan, because that actually also related to the wind turbine, what you call lifespan. So IGBTs usually lifetime is 10 times the IGCTs. Okay, so this is also very important, because when we calculate the lifespan of wind turbines, we include we take it based on the lowest the lowest lifespan of component within the system, because there is for example, there is a gearbox, there is a generator, there is a power electronics, there is a rotor. So which one is the lowest? And that's actually determines the lifespan of the system, because it fails. If it fails, the system fails. So that's what we call the lifespan, or sometimes you call the warranty within that time, 10 to 15 years, for example. And then also one thing is good about the IGCTs, which used in converters, is they have 2 times lower losses during the turn on, and that's actually quite significant, because if you have turn on, means the efficiency increases of these converters if we use the IGCTs. And this table actually summarizes, so the comparison for the wind conversion summarizes the difference between the IGCTs, IGCTs and MOSFETs. For example, here we have 4. We have the IGBT module, IGBT press pack. Module means a single unit. Press pack means there are maybe 4 or 6 IGBTs within one pack. IGCT press pack, and then we have silicon carbide modules or MOSFET. Okay, so in terms of, if you look into, for example, the power density, they have quite high, very high, because it's a pack. Okay, in terms of reliability, it's moderate, it's quite high, it's high, quite high because the IGBT, we compare it apple to apple, you know, IGBT press spec with the IGC press spec. Okay, in terms of cost, it's high, both of them high. In terms of failure mode, short circuit, yeah, they short circuit. Yeah, this is requires snubber circuit. This one does not require, which is good. Small, moderate. Okay, here gate drive. Okay, gate drive. Okay, to drive the switches is moderate. This is large. Okay, so major manufacturers who do this, you know, the big players, ABB. Here also it's ABB, and you can see the voltage rating here for the IGCT. Usually it's higher in terms of voltage. So it is very clear actually that IGCTs can handle high power, but they have some disadvantages, you know, in terms of gate drives and so on and so forth. So we find both of them in industry. Both of them are used. Some are more recently. Most of the power electronics in wind turbines is what we call IGBT based, okay, rather than IGCTs. Okay, so what are the technology challenges for power electronics in wind turbines? So where is it? Let me come here. So what are the technology challenges, okay, for power electronics in wind turbines? Okay, so what do we need? We need the more advanced power electronic technologies, okay, to improve the wind behavior, wind turbine behavior. And I'm not sure I have shown you the slide. Let me go back here. Yeah, I think I have shown you this. I'm not sure. So the use of power electronics in wind turbines. So you can see here in the start of the 80s, okay, almost zero power electronics. The use of power electronics rating around zero, and then it's moved to 10%, usually used in the rotor synchronous just now, rotor resistance, and then rotor power, you know, the defect, and then now we are moved into from now onward we are moving to almost 100% what we call power electronics driven wind turbines. Okay, so let's continue here. So there is a need to improve the performance. I think grid integration, there are still issues to be addressed, and that's actually due to the power electronics also, especially the fluctuations and unpredictable features of wind energy. And this can be either we use forecasting, or we use what we call prediction, whatever, you know. And this is not only from the source side, but also from the load side. Okay, so predicting the load and predicting the we have quite a good, actually quite accurate, good load predictions, you know, because a lot of data. Okay, however, from the wind, still we have quite, we still need more. The individual wind turbines must be able to control the active power at the PCC, the point of common coupling. So that's actually also for grid integration. The reactive power delivered by the wind turbine also have to be also regulated. So this all ensures what we call grid stability, and also good integrations for the what you call the system. Okay, and the objective for all is to make sure that low energy cost, because we don't want to generate something which is more expensive than the conventional energy sources. Okay, we need to have a high reliability, because people always questioning how reliable is your energy sources that you use from renewables, and also for better grid integration. So these are all have to be combined in order to make sure that actually the future what I call power or wind power in grid works. In terms of integrating, as I said before, integrating it into microgrids, this is much more maybe less challenging and less complicated compared to integrating it to the microgrid. However, the issues is still the same, but with a lower scale, especially if you have a lower systems, which is can be isolated, and the microgrid can work independently. I think maybe we leave another 5 minutes. We have another 5 minutes. Maybe we open it for questions. Any questions so far? Anyone have any questions?
Professor, can you emphasize on the reactive power WTS?
Sorry?
See, in the last slide what you have presented, the reactive power control.
Yep. Which one?
Yeah, the reactive power delivered by WS also has to be regulated.
Yep.
Is it the wind turbine is going to generate the reactive power?
Yes. The wind turbine have to be able now, because we are moving from centralized control to decentralized control. Okay, so based on the information received from the grid, then the grid, the wind turbines or the generators or these distributed generators have to regulate this from its side. For example, how much power, how much, and as I mentioned before, with the introduction of this grid forming inverters, the inverters are also responsible of the amount of to regulate not only the active reactive power, and even also regulate the voltage and frequency. Yep.
No, but in the case of the double-fed induction generator, the grid side converter used to generate the reactive power required for the generator.
Yes.
No, in that case, like the wind turbine or the wind is not going to the induction generator, which is there, is not going to generate the reactive power to the grid.
Yeah, correct. Yes, true.
But for this point, I am just a doubt that the wind turbine system is going to deliver the reactive power to regulate the grid. Is it?
No. These are the challenges.
Okay.
Yeah, these are the challenges that need to be addressed. Yeah. These are not the current, but these are the challenges.
Okay.
All right. Any other questions? I think I've explained this just now for the. I think this one we mentioned this. Yeah, I think we mentioned this. I think we mentioned this fast and slow control dynamics. I think we have explained this, but I'm not sure. But you can see if it is a fully power electronics or converters driven wind turbines, it all goes back to these converters PWM control that's been generated in terms of either grid synchronization, voltage, frequency, voltage and current control. Even like I mentioned just now, the MPPT, the inertia emulations, energy storage. Like if we have extra. Because as I say, most of these wind turbines now, most of wind farms comes together with storage, which large. We're talking about megawatt level storage systems. So, and these integrations need to be, taken in consideration. So, how much goes to the storage, how much can go to the grid, and so on and so forth. All right. Any other questions?
Participant, do you have any questions? This particular topic is a very interesting topic, and where you can really do much research also.
Yes, I agree. Because there is a high demand on it actually, and there are a lot of issues to solve also. There's a lot of issues to address in this. There is quite what I call interesting areas of research in this.
Professor, I have one more question.
Yeah, please.
When you're going for a modular converters, is there a thing of circulating currents between the two of the?
Yes, yes, very, very important. Yes, that's we'll have automatically. We will have for this. We will have circulating current. So, but you need to devise, the control system to regulate the circulating current.
Okay.
Yes, very, very true. When you have a modular which is interconnected, yes, you will have a problem of circulating current. Very important. But need to, I think I have, let me show you. I have one PhD student who works on this. Scott. Maybe if I can find it, I will share it with you. Stop presenting. Let me check this. Hey, please, others, please continue, ask questions if you have. Let me look for this not this one. Yeah, this is just to address the issue of the circulating current.
Professor.
Yes, sir.
Yeah, is it possible to you on tomorrow maybe deliver on the droop control of voltage and frequency, maybe something around 10-15 minutes?
Yes.
Yeah. Yes,
yeah, tomorrow we have some, yes, so some control. Yeah. Let me. Yeah, this is the one I think. Yeah. But we use that. We use this one for PV, not for the.
Yeah, PV one. I'm talking about the PV one.
Yeah, let me show you this. Present. Entire screen. Screen number 1. Share. And then take the PowerPoints.
Yeah.
And then showing here. So this is one of the work actually we have done in our lab, where we have modular multi-converters for grid connected, large PV, and also can be used for wind, for wind farm. So what we did actually, you see here, this is using hitch bridge, okay? So automatically you will have a problem of circulating current, right? So, but what we propose this new topology, and then we have two issues here. One is the energy balancing, because you have systems which supplied by two systems. Maybe the power, maybe one part is shaded, another one is not shaded. So we address the problem of what I call energy balancing, okay? Which is this is energy balancing strategy. And then this is we test the system's dynamics and performance. For you see the circulating current you mentioned just now. You see the arm circulating current, we all maintain 0. So here, when there is an arm here, there is a circulating current, and then we maintain it to 0. So yeah, that's very interesting. When you're having this kind of modular converters connected together, you will have this problem of circulating current, and especially if you have a wind farm or whatever, so this can be also used in wind farms, when you're having two wind turbines which having different wind profiles. Yep. All right. Okay. Any other questions?
I think no questions, Professor, from many participants. Yeah, just a minute. I think.
All right.
Yeah,
that's good.
Yeah, thank you, Professor, for wonderful.
Thank you very much. Thank you very much. Thank you very much, and see you tomorrow then.
Yeah, fine.
Thank you. Let me stop sharing.
I forgot. I one more thing that.
Oh. Cancel. All right. Thank you very much.
Yeah, thank you, Professor. We'll have it. Okay, Professor left. Okay. I'll share the attendance link. Okay, everyone have given attendance. Gayatri, interview outline. Just a minute. Participants,